I'm Perry, and I work at Microsoft. I'm a technologist there. I'm working on advanced architectures. And I also am founder of two startups, one of them being Rumble and another being a computational vision. Aside from that, I also do some authoring, but today I'm going to be talking about the way we've been computing for the last 70 years. And I'm going to talk about 4 different architectures that I see pending, and what that means not only from a hardware point of view, but a system point of view and a software point of view. But in all my training, which has been in industry, you always start with a problem you're trying to solve and then build a technology. I've worked in areas where we built a technology and tried to find a problem, and that has not worked very well for me or the company. So let's see if we can move on. So I'm going to start with a statement that every computing problem is genuinely the same. And I've worked in areas of, I associate myself as a computer architect, but I've worked in areas of imaging, I've worked in areas of computer vision, semiconductors, even IoT devices, and high performance computing. And from a software point of view, when I look at the problems we're working on, there's different domains of problems, but essentially they're all the same. And whether you're starting with a Turing machine or starting with a problem you're trying to solve in an office computing environment or even an HPC environment, a lot of the problems are genuinely the same. So when I think about computing problems, there's the element of data generation and then the element of data motion. And my parents worked in the press. They worked in the newspaper industry for a lot of years. They were the sources of data generation. And I worked when I was a little kid as a paper carrier, and I would deliver that medium. Every problem that I see is genuinely the same. You have sources of data generation and sources of data motion. So when I look at these architectures, I have to go to this guy, and there's just a little history here. When I was a kid, about, 11 or 12 years old, I went to a used bookstore and I got this book. It was called The Computer and the Brain. I thought that was kind of a cool book. And I got it for, I think, $1, maybe 50 cents. And I didn't really appreciate this book until I got about 20 years into my own industry. This is written by a gentleman called von-Neumann, and he was a Hungarian mathematician, you may know him, and he had a lot of contributing work in the areas of math. But what I'm going to talk about is the von-Neumann architecture. And when he immigrated to the United States, they needed mathematicians that would work on the Manhattan Project. And he happened to be a very well-regarded mathematician, and they needed models because you're not going to detonate the only warhead you have to go and understand it. And he used a machine called the EDVAC. And the EDVAC was an Eckert and Mauchly design. But what he's known for is authoring the book on how that design works. And it was, this is one of the very first types of machines after the UNIVAC, back in the 1940s, late 1930s, is based on vacuum tubes. It used 56 kilowatts of power and consumed an entire floor space about the size of this room. And he published a book, not that book, but a book on the first draft of the EDVAC architecture. And this is where what's known as the von-Neumann architecture was founded. This is what we have been used to in the areas of computer science and computer engineering for the last 70 years. And so what is the von-Neumann architecture? And on the left, basically you have a computing element, an ALU, an arithmetic logic unit, and a bus and a memory unit. And when you look at every problem, every computer, every device you have on yourself right now, your phone, your computer is basically the same. You have a computing element, a processor, maybe an ARM or a Intel processor, a bus, an interface, and some kind of DRAM. And when you look at every problem, One of the fundamental challenges is that data generation, which you can attribute to the processing device, and then the actual transportation of data. And that would be to commodity DRAM, to a storage component, even to a cache. And this is fundamentally how you think about problems, from an architectural point of view to a programmatic and system point of view. And we've been building computers, and it's been quite successful for many, many years. So the von Neumann architecture is now known as the von Neumann barrier. It's the memory wall. So what this graph shows here is essentially a statement that says flops are free. So your floating point operations, we've been writing Moore's law. We've been building systems that can take advantage of transistor density and approaching and making use of Dennard scaling to improve the power of a device. And you see NVIDIA devices and you see Intel devices, and there's been a near linear scale in the ability to move bits. Basically, the number of flops, number of operations you do on a unit of data per byte of access. So if you access a byte of data in a cache or in a DRAM, this is how many operations you can do in it. This is good computer architecture. This is everything that's built on improvements of a microarchitecture and in the silicon design of producing faster parts. So if you look at a modern design, this is a processor from Marvell called Marvell Armada. What they do to make use of this and to extend Moore's law is it's a heterogeneous design. I mean, essentially, you have different types of computing elements. You have CPUs from ARM or from Marvell. You have DSPs. You have microcontrollers. You even have silicon that hardware designers have built for a fixed purpose. But I argue that even these architectures are all the same. You're taking data, you're processing data, you're moving data. So the problem right now is we've made use of heterogeneity. For example, you might have a traditional CPU to execute legacy code, to execute unpredictable patterns of code. So if you have spaghetti code or whatnot. And it also offers all those microarchitectural improvements for more and more performance. You may have fixed function silicon if you have a dedicated I/O, or if you have an algorithm that's uniquely systolic in nature. And so you might have force your algorithm from hardware or from software into hardware. You may have a GPU. GPUs are quite popular right now in HPC and in other areas. If you have embarrassingly parallel and symmetric multi-threading is a de facto standard. Or you might have a microcontroller. When you're cost optimized, when you're thermally optimized, and when you need something that can actually process a deeply embedded problem very well. Or you might have a DSP, where you have a stream of data and you're looking for patterns. You're looking for everything that a GPU would be too heavy to do, a CPU would be too large to do, and you might have a DSP for a signal type of problem. But even those are all the same. So here's Moore's law. And what it shows is the discrepancy between the performance of traditional silicon that you get in a processor and memory performance. I think a lot of people have seen this. We have drastically improved CPU performance, as I had shown. But memory performance has been linear. And that trend has challenges. So if you're designing a CPU, you basically have a set of tools and a set of problems and a set of challenges that you go down, and you can produce silicon. If you're designing memory, it's a whole different domain of science. And I worked in both areas. I worked in companies producing silicon and companies producing memory designs. And the von Neumann architecture has drifted these two domains of technology apart. In a memory design, you're going to have very custom design tools. And in a standard CPU, you you're going to have standard design tools, standard libraries. There's going to be layers of abstraction that you use when you define that hardware. I started my career in logic design, and I moved to memory design, and I was very surprised that memory design uses tools that are very analogous to analog circuits. You also have transistor sizes. So in a CPU, your transistors are going to switch very fast. In a memory design, they're going to switch very slow, orders of magnitude slower. In an SoC, because of the various levels of abstractions, you have less density. You actually have much more density when you look at a unit cell in a DRAM than in a CPU. And you also have different power curves. So you have very low leakage in a DRAM design, and you have obviously leakage challenges much more leakage challenges in an SoC design. So these domains have universally been bifurcated, and I'm going to propose something a little different. This is from Exascale channel by Shekhar Borkar at Intel. But what this demonstrates has been going on now for the last 20 years. And it shows the amount of energy that's used in moving data from a CPU or a DRAM. And what you can see is that even in our current chips, 7 nanometer chips are coming out and 10 nanometer, a bulk of the energy in computation is simply moving data within a chip or moving data between DRAM and memory. And it's also getting much more expensive. This is much more meaningful to me in my industry because we actually hit the sweet spot in CPU design when we went to 28 nanometer nodes. Now it's actually getting prohibitively expensive to actually build a new chip, build a new foundry, build something that's economically viable to go to reduced nodes. You have to increase your volume to get better yield. You have to increase your factory space, the number of process steps and whatnot. So you have to make decisions now on whether you're going to do that chip or not. So this is the end of Moore's law, and even Moore himself on the right-hand side speculated when his own law will come to an end. This is from The Economist. And you can hover around that. We're gonna bottom out somewhere around 2020. And this has to do with the thermal design and the number of transistors. The transistors are interesting. The actual number of transistors on a chip is increasing linearly. What's happening in chip design is that you now have dark silicon. You have areas of a chip that are simply unused because you can't power the entire device simultaneously. Or you have to go to very advanced thermal designs to get all that heat out. So the problem. So I wanted to talk about, well, these designs in your current architecture, in your phone and your computer work fine ad infinitum if you never had a new problem, if you are dealing with the same type of data. But that's never the case, right? We actually have different types of data and different types of problems that we need to solve in going forward in the next 10 years. And the obvious case is increased resolution, increased video density, increased unstructured data in the sense of moving from 1080 to 4K to 8K. The plurality of data is in that space. But there's other interesting areas too. For example, hash reductions for blockchains. And this is what drove the demand for NVIDIA GPUs in Bitcoin mining. Machine learning inference, not only in self-driving cars, but for anything that's looking for predictive analytics, understanding the unstructured state of a video or audio or in industrial IoT. And of course, IoT with more devices being connected through 5G services. And an interesting area of a problem that I've been exposed to is unstructured data mining, looking at all video sources, at all Twitter feeds simultaneously and looking for patterns. These are substantial amounts of data. There was some research I did earlier last year looking at, well, how much data are we actually generating versus how much data can we actually move? And this is the data generation, data movement problem. And I looked at about 100, maybe 120 different data sources, everything from analog information back to the 1970s to digital information from a number of sources. And what we see here is that year over year, there's a 20% growth in the amount of data that's produced versus the data that you can move. And there's a lot to attribute here, and there's a different talk, a different paper on this. But this has increased year over year, a 20% delta in data generation. So there's a problem. This is, I always start with the problem side. So the last time we've had new architectures, it didn't go so well. I actually labeled this slide the Dead Computer Club. And there's a lot of industries here that just kind of faded away, got bought out, or dissolved. Certainly, Intel still exists. But this was the heyday in the early 90s, maybe back into the mid 80s, when you had esoteric architectures. But the common theme here is that a lot of those architectures had problems. This is the top 500 supercomputer list. And what you see is that in the early 90s, you had 17 disparate computer architectures. And that has whittled itself down to 5 unique architectures in now. Actually, it's about 4. Mostly they're going to be x86 related architectures and GPU architectures. So why is that? Well, you've had a lot of novel types of architectures that have existed. Businesses have formed around them, but those businesses don't exist. There's a lot of reasons why. I'd be glad to have a discussion or debate with you on that. I have my own opinions of why they never morphed. And one of the reasons is that what is the business case? What is the monetization of making this new architecture a reality? What's the problem? So what I'm seeing now is the new renaissance, the 4 architectures that I actually think have meat on the bone, so to speak. So what I look at are neuromorphic designs. You probably have seen some of them from IBM, True North, for example. Systolic arrays, I'm going to talk about those shortly. That had a heyday at one time in the late 80s. Computing memories. These are a way to break the von-Neumann barrier by not moving data at all. And of course, quantum computing, which we'll hear a lot more of at this conference and tomorrow. So neuromorphic computing or cognitive computing, however you might define it, there's a number of companies, large, small, startups, and well-founded companies working in the areas of neuromorphic. This is the True North chip. This is a government-sponsored or government-sanctioned chip. And basically, it's dealing with phase change or NAND flash memories. And the way this works is it's basically a technology called leaky fire and forget. So a cell would be composed of a phase change memory or some kind of persistent non-volatile memory, and you can drive that cell through basically spiking. The same way a neuron works, the same way that a brain works. It's a brain-inspired computing architecture. So they run very slow, but they could be very dense. And that's the intent here, is that the architecture here, which was a US government-sponsored research project, is to have a density of about the human brain. Now the applications for this are interesting because it falls right in line with machine learning training, but also machine learning inference. It's very good at graphing problems, matrix math, types of problems where you have an ordered set, a linear matrix that you can compute on. Now, the bottom graph here is my explanation in so many words of the programming model and the fabrication cost. So coming from industry, you always worry about cost, but you also always worried about a programming model. I've seen projects fail, a lot of those computer architectures, including my own, failed because there was no software acceptance. The programming model for a neuromorphic machine is very unorthodox. It's not going to be what is common to a new computer science graduate. And the fabrication cost is somewhere in the middle. It's going to be relatively high compared to some of these other architectures that I'm going to elaborate on. The next architecture I'm particularly fond of, it's called data flow computing and systolic arrays. And what these devices do is you feed them a sequence of data. It could be a pattern, a signal. It could be the entire Twitter feed. It could be packets. It could be anything for genome sequencing. You can look at it as a genome as a sequence of bits. Anything that you have where it's a sequence of bits, it can be fed into a data flow systolic array. And what these do is they operate on a stream of data. And it has a reconfigurable network to go and perform logic on that stream. And the stream can form substreams. So there's companies that have products and that are working on this. For example, Wave Computing, Maxeller in the UK, and Natural Intelligence Semi, which was a spin-off of Micron in Boise, Idaho. The programming model here is what you see in the bottom left. So this does not look like software, it looks like code, it looks like states. And what you're seeing here is a genomic sequence looking for a particular set of states or events or patterns, and that is exactly how you would program a device like this. So you're kind of getting a theme here, a theme that these architectures can solve problems, and I haven't revealed how well they solve problems, but it's going to be a very unorthodox type of mode you have to be in to actually program it. The next architecture that I'm particularly fond of is processing and memory. This architecture is essentially using DRAM or SRAM or things that are memory and performing the computing as close as possible to the cell that stores that data. And in an architecture like this, on the top left, this is from a device called the IMI that I worked on at Micron. This has computing elements within the bit cell. So you don't move data, you compute on that data on that bit. So essentially, it's a 1-bit computer times 2 billion bits, and you have basically 2 billion very small Turing-complete computing devices. So what can you do with that? Well, this has application in certain industries. It's very good for certain types of applications, and it is very, very bad for other types of applications. Use the right tool for the job. What we found is that machine learning inference, but not necessarily training, is very good for this type of device. Things dealing with matrices, matrix math, convolutions, imaging and vision, genomics, sequences. Everything that a data flow machine can do, a device like this could do. Two companies that are working on this are, one is called UpMem and the other is GSI Technology in the Valley. And in this type of architecture, the programming model is, it's very common. It's C, C++, it's standard programming languages. And the application and cost can be very low because it uses the same manufacturing steps that you use in creating DRAM. So that curve that you saw where you have DRAM designers building analog circuits, and it's a completely different domain than building a CPU, they can actually build a device like this. The final architecture is quantum computing, which we'll talk about more. And there's a number of companies working on this, D-Wave, IBM, my own company, Microsoft, Google, Intel, and so on. And these are, there's a lot of vested interest in this, a lot of government-sponsored interest in this. And it is dealing with a certain type of problems that can be represented in basically qubits of state. And the way that you traditionally build a machine like this, it's not at all like a traditional computing device, piece of silicon that you would have in your phone or at home, is that you basically are taking a device and cryogenically freezing it. And you pass a Microsoft pulse through this device that changes the quantum state of a qubit. So you're dealing with quantum information at this point. You're dealing with changes of state that have relationships, that could have a superposition and dependence on one another. And it's a statistical computing model. And what this allows you to do is it addresses certain very, very fundamentally rooted problems in information theory, in obviously in decryption and security, in random number generation, computational chemistry. But to use a device like this, the programming model it's starting to get a lot better because there's libraries and interfaces that allow you to program this machine. And the fabrication cost is very high, though. There are some challenges in the maintaining the state and controlling noise in a system like this. But there's a lot of funding and a lot of research in this area. Now, all these architectures share one thing in common. They're non-von-Neumann architectures. You're not moving data, or you're moving data very infrequently between a memory system and between a computing system. And that is where I think these architectures are going. So in the next 10 years, this is my final slide, we have to accept, and I have accepted, and I have fought this problem when I built a lot of silicon in my life, is that every problem is the same. It's a von Neumann barrier problem, moving data back and forth and find more efficient ways to do that. So this non-von Neumann problem is here, and the business case around it is that we are generating much more data than we have the ability to process or move. So what do you do with all that data? And the other problem, which is the real killer problem here, is building a software, not only industry, but also new tools, new frameworks to actually ease the burden of using a device like this, because there's going to be a very non-traditional way that a device like this is used. And that's where the academics come in. When we think about computer science, when I was working on my computer science undergrad in the mid-'80s, it was a very traditional way that you express data and you compute on data. What you've seen here is just a touch, just a high-level touch of these types of computing devices are going to be very, very different. And for someone working as a data scientist, so for someone working with this type of data, they'll have to be retrained and retooled themselves to understand and use these devices well. And I think that is it. Well, the call to action is basically what I just said on the last slide. You have non-von Neumann architectures, you have data deluge, and so we have to work on this problem as a community together. Thank you.